a long time, but it really is kind of zoomed by. So therefore, like, don't have the wrong perception of how much time you have left to prepare for your finals and get all your stuff done. It's going to go by quickly. Don't waste any time. This weekend is pivotal, and so is next weekend. Like, you don't want to just be cramming it all in those last few days before the final. You want to learn this stuff. Some of the classes, obviously, you guys are taking are asking you to learn everything again, right? You have cumulative finals, so like you have to cover everything. You have to start now. You can't leave it till the last moment. So make sure that you guys are doing that. Again, it's all about walking away feeling good about what you've done here. You've signed up for school. You paid fees. You endured exams. You read things that maybe you didn't want to read. You did a lot of stuff, and like, to make that all worth it, like, you want to get a solid grade in all your classes. And if you don't do that, then why are you here? What are you doing? That's ultimately a question you need to be asking yourself. And if the answer is like, I don't know, then figure out what you are doing here during the summer, and make it work out for yourself. Like, if you're here, you have to be committed. You can't just be half here. Like, again, it's not a matter of just checking off a list of classes you have to take to get your degree so you can write it on your resume. Like, that's not what this is. That's what high school was. You just did what everybody told you to do, and then you got your degree, and look, I got my high school degree. But here, like, it has to mean something. Like, your college degree has to mean something. You have to make it mean something, and the only way you make it mean something is by actually working hard here and letting that transform you into that kind of person, the person that is always a go-getter, always trying to hit the highest marks, always putting in as much time as possible into everything you take on. That is the most valuable thing that you can learn to do at the university. So let it happen. Let it happen by, just completely investing yourself into this process, jumping in head first. Like, don't shy away from it. Don't be afraid of the hard work. Don't be afraid of, like, not being able to go out and doing all these other things you want to do. Those things will be done. You will have time for those things. Like, this is not the time for it, especially right now. This is not the time for it, these next few weeks. So keep your head in the game, folks. All right, so as far as what we're doing here today, we are going to finally finish off chapter 10, and then we're only going to have the last two chapters to cover. Chapter 11 deals with sort of more practical ideas that allow a firm to use some of the knowledge we've generated via analysis of markets to apply some of the principles in a more practical way if the resources aren't available, to hire economic consultants or do economic research that would allow you to generate the kind of information you need to be able to do the kind of analysis we've been talking about, the demand curve, the cost curves, all that stuff. Like, you may not have the resources to be able to be as precise about it as we've been in this course, but again, this course is about developing like basic intuition about how these things work, and then in practice, obviously, a lot of it is like creativity, a lot of it is like you kind of thinking on your feet, but you have the starting point. You have the sort of basis for like how all of this works in general, and then you kind of just work from that, and it allows you to be a more effective person in whatever you take on within the realm of management. So in the next chapter, we'll learn a few things that help us, individuals that may not have the broad resources that larger firms have, to be able to do some of the analysis we've done in a more practical way. And also, we'll talk about price discrimination, which is the ability of firms to charge different prices to different customers, and other kind of strategies that firms that have market power are able to take in order to, basically take more advantage of the markets they engage in by seizing some of the profits that are available that are generally just kind of left to the consumer as consumer surplus. So we'll talk about those different things. And then finally, in the last chapter, we'll talk about issues having to do with information. Everything up until this point, most things have been done under the analysis and assumption that everybody knows all the information they need, and obviously that's not realistic. We don't always have all the information we need to do the kind of analysis we're talking in this course. And so we'll slightly touch upon some of those issues in the final chapter. Those are more complicated issues, and that's why ultimately the stuff that we cover here, to really become a true master of it, you need to go further. You need to broaden your skills in math. You need to broaden your skills in statistics. And at the master's level, you kind of advance your understanding of how all of this is done in practice in order to account for the complexity of the world that, it has more than a couple of variables affecting demand. It has like all the variables affecting every variable we've been talking about. And of course, to be able to extend the principles that we've developed here to the more complicated cases, you need the more complicated tools, which are ultimately what is used in practice in the larger firms that actually do all the stuff we've been talking about to try to optimize their firm behavior. So we'll lightly touch upon some of those issues about uncertainty, and both on the demand and the supply side, and then the final section in that chapter has to do with bidding on different types of auctions. So it's kind of an interesting topic, and sort of what are the optimal bidding strategies. And then we'll be done with the course, and then you'll just have an exam, and then you'll never have to see me again. So we're getting there. We're very close. Of course, the paper is also something that's coming up. Chapter 10 will be done today, so I'll leave the mini paper open until next Thursday, but that will be the last mini paper beyond the open chapter, which I think is due Sunday, on the 30th, which might be Monday, actually. Is it Monday or Sunday? It's Sunday. All right. So that's it for that. Spend next week doing what I've told you a couple of times already, to get your final paper finalized, or maybe just get it done this weekend, or maybe you already got it done, which is good. I did not set up an option for you to submit the final paper, or did I? I did not. Okay, so I'll do that today. I did for my other 308 the other day. So I'll set that up. You can start submitting them digitally, but as far as the hard copy goes, like I said already, you should turn it in to me by the due date, which is a week from Tuesday in class. So that's the only time I'll collect them in class, but if you want to turn it in before that, you can turn it in to me during office hours. You could just slip it under my door anytime. In my office has a little slit under the door. You can just slip it under. It'll be safe. It's my office. It doesn't belong to anybody else, so it will be fine. Just make sure that you write on there that you are in 308. That means Tuesdays and Thursdays, or else I won't be able to know what class your paper's from, and it could get lost. It won't get lost, but it'll create problems for me. I'm gonna have hundreds of papers to look at. So, all right. Are there any questions about anything at all you want me to talk about before I talk about the actual material we're going to cover today? All righty. All right, so we're finally going to finish off the game theory chapter. Again, this is a very powerful approach that helps us to sort of maneuver through complicated situations where there's interdependence in decision making. My decision depends on your decision. Your decision then will affect my decision. So that's complicated. That's not something you can easily just like have a rule for, like you need more complicated analysis for that. That's why we had the last chapter that kind of had different ways of approaching the oligopoly context, which is what we're ultimately talking about here. But this tool, game theory, is used to sort of broaden our understanding of how firms can manage their way through these complicated situations. And so it has to be a little bit more complicated to be able to deal with that. And that's why we've seen the escalation of the complexity of what we do here. And it's also why I don't make the final cumulative, because again, like the last section has enough challenges, and really most people, if you make a class like this cumulative, like will not learn the last material well enough, because they'll be scrambling to get everything else down, and then things will fall through the cracks. And I know for a lot of you this class is trivial, but for some people, like, the information is pivotal, like for their advancement to move forward to whatever it is they're going to do. This is foundational for them. And so it's important that everything be covered and people have the time to learn it and and again, that implies that you will require a good amount of time to get this stuff down, and so that therefore you should spend that time, which is again why you should really take advantage of this weekend and the next weekend before finals weekend, so that you can really start just understanding all of this, getting it down, and then you won't be leaving half my exam blank. Like just don't leave the exam blank. Like, come on, folks, like learn the stuff, do your best. I want to give out good grades to everybody. I want to see really strong showings at the end, so do it. Do it for yourselves. It makes me feel good when I see people do well, so please, if you don't do it for yourselves, which you should, and that should be really the only reason, do it for me. I know I don't matter much, but Anyway, all right, so we're going to finally finish covering the last couple of sections of the chapter. Again, we talked about how the oligopolies that maybe are stuck in the Bertrand trap, as it were, where they engage in a price war and they have to price down to marginal cost and make zero economic profit in the long run. Those firms can maneuver their way out of that situation, and it depends on the nature of the interactions with their rivals. If the market is going to be one in which they're going to be competing indefinitely over time, or even if they are competing a certain amount of times that they don't know, even though they have an understanding that it will end, they don't know exactly when it will end. And the thing and that will lead to the same result. So that will lead to the firms being able to sort of get out of what we talked about as the prisoner's dilemma, where again the firms are kind of stuck in that Nash equilibrium of the one-shot game. So they as long as like either the interest rate is high enough or the probability that the game will continue is high enough, then they are able to sort of have what's called tacit collusion, which basically means that they start behaving as though they have an agreement to limit output and have higher prices, and just kind of do that until somebody breaks that pattern, and then everybody kind of reacts and then starts charging lower prices, and that's when the price war would get engaged. So that's called the trigger strategy, as we talked about it in this class. It's also called tit for tat. And it is, again, the way that these firms are able to escape that trap that is easily fallen into in certain oligopoly settings. So we will finish covering the case where the game has an end, but the last case we have to consider is the one where they know when the game will end. And when they know when the game will end, when they know when the final round will be, then that sort of unravels their ability to work together tacitly. And we'll talk about why. It's called the end of period problem. And then finally, we'll cover the last approach that we use in game theory, which is probably the most powerful one, but the least applicable to the oligopoly case. But nonetheless, it can provide some insights in this course, and that's why we'll cover it, in which the players don't make the moves at the same time. They make them sequentially in stages. So like one player makes one move, and then the next player gets to respond to that. And so that creates a new kind of set of complexities that we'll lightly touch upon via some examples. You'll just kind of get a bare bones introduction into the approach. It's very cool, ultimately, in practice, the approach. You kind of make a game tree, and you kind of branch out all the different possible strategies, and then what the strategies are that one will respond to original strategies, and that creates new branches, and then you can go really far with it. You can incorporate probabilities into that as well, and it winds up providing really important insights into, again, situations that normally you wouldn't be able to have like a solid prediction about. You wouldn't be able to say, well, I don't know exactly what's going to happen, but these are the things that are likely to happen. You wouldn't have that without this approach. And you'll find it in most like advanced sort of analysis of any type of complicated situation where there is interdependence and decisions are being made, sequentially. Again, like it's the sort of thing that has made a big impact, but in this class, it'll seem kind of trivial because we're only going to cover it for a slight amount of time. All right, so just as far as we covered last time, I'm not going to review the whole chapter again because I've done that twice already. So I'll just start with what we covered last time with the infinitely repeated games. Again, that is a game that is played over and over again forever, as opposed to the section before this, which was the stuff we covered last week, which was the one-shot interactions, in which the moves, the players met once and the moves are made at the same time. So that was a one-shot simultaneous move game. So these are still simultaneous move games, but they are played infinitely, an infinite amount of rounds. And so when we are looking at the situation we've been looking at, which is, again, is there incentive for the firms to cheat on agreements that they could make to increase their profits? And we identify the fact that, yes, there are, and so they would. But and that happens in the one-shot scenario. But if they play the games repeatedly, then they have to weigh the cost versus the benefit of cheating. The cost of cheating is going to be the present value of the profits they make into the future that they would reap from every round from being able to collude either implicitly or explicitly with their rivals. And so that's why, again, we talked about just a quick review of present value and how, like, an income stream that goes indefinitely into the future with each payment being the same can be represented by this sum here. So this sum will equal this amount, the amount of the profit times 1 plus the interest rate over the interest rate. All right, so again, like I mentioned, collusion can be sustained via a trigger strategy, a strategy that is contingent on past plays of players in a game. A player who adopts a trigger strategy continues to choose the same action until some other player takes an action that triggers a different action by the first player. So again, the firms in these Bertrand pricing games want to be here. They want to be working together, charging a higher price and getting higher profits, but there is an incentive for each of them to cheat, charge a low price at any given time, reap higher profits once, but forever after just make $0. So they again have to consider the present value of the income stream versus the amount they would gain from cheating just the one time. And the income stream represents, again, the opportunity cost of cheating, right? It's like the money you're passing up by not abiding by an agreement. And so we figured out that as long as the interest rate is low enough, then at least in the situation we looked at, and really it does extend to the more realistic cases, as long as interest rates are low enough, then firms do have an incentive to abide by these agreements, be they set up, again, illegally, explicitly, or tacitly, implicitly. Because, again, like, if the interest rate is low, that means that future profits aren't discounted that much, and therefore they have more value in the present. But if the interest rates get really high, then future profits wind up not having as much value, and therefore current profits from cheating might outweigh that, therefore making it worth it for the firms to cheat, which is what all of this means. Then we talked about, so therefore if that is the case, then they do go about what's called tacit collusion, which, again, like, they just kind of go about their behavior as though they had made an agreement to charge the higher price without actually getting behind closed doors to do it, and just kind of feeling out if everybody else is doing the same thing, and if they are, everybody just kind of continues that until somebody does something other than that, and then the trigger is pulled, and then the behavior changes. So in practice, we talked about the few factors that actually affect the ability of that to happen. One of the things is the number of firms in the market. The more firms that are in the market, the more the firms need to monitor each other. If the cost of the monitoring gets too high, then that will eat into the profits. And so that could offset the benefits of not cheating, and that might cause cheating. Firm size, the larger the firm is, the lower the cost. There's an increasing returns to scale to monitoring. So if you're bigger, then the amount you have to spend on monitoring is less than by a smaller firm. The history of the market, again, that's what allows for tacit collusion. If everybody's kind of behaving the right way, then tacit collusion occurs when the firms do not explicitly conspire to collude, but accomplish collusion indirectly. Again, just kind of behaving as though they had made an agreement. And of course, the punishment needs to be credible. So if you're threatening to punish the other players in this oligopoly game by charging low prices forever after, if they do that, then you need to be able to follow through with that. And if you're not, then obviously things fall apart. All right, then we talked about finitely repeated. So that's the infinitely repeated game. That's when the rounds are indefinite. The firms are competing forever, as far as they know. Their products are forever going to be viable. People are always going to buy them. You know, toothpaste, cars, like things that people are always going to buy. Well, cars might become flying cars at some point, but they'll be cars. Anyway, so as long as the firms don't know when the game will end, everything's fine. In an infinitely repeated game. And so that translates then into the finitely repeated game, where the firms don't know when the final period is. They know that the final period is coming, so it might be a situation, one of the examples we looked at was like cigarette companies, like maybe the government is like thinking of banning cigarettes. So there's a chance that they won't be able to sell their cigarettes anymore at some point. They don't know when it's going to happen. If they don't know when it's going to happen, then again, all they can do is kind of approach the market by, again, looking at the benefits of cheating versus the cost of cheating. And again, the cost of cheating is the foregone profits that they would earn if they just kind of colluded together tacitly. And so another variable that comes into play when there's an uncertain final period is the probability of the game continuing on. And so we looked at here, this is so we said that theta is the probability of the game ending the next day. And we did some analysis here, and we established that as long as the probability that the game will end tomorrow is low enough, then again, they can sustain the same kind of tacit collusion, because again, like they have an incentive to keep moving into the future, because those profits in the future are likely to happen, because there's a low probability that the game will end either the next day or the day after that or whenever. But if the probabilities are high, then even though you have sort of this foresight of like this income stream that's going to happen into the future, and each round you'll make extra profits, because there's a low probability that will actually happen, because the game could end anytime, then those profits are discounted more than present profits. Like the probability acts like a discount factor, where again, it's just like sort of a psychological perception thing, where profits in the future aren't worth as much as profits today because they are unlikely to happen. And so we assumed in this section that the interest rate was equal to 0, just to kind of highlight the nature of that probability's role in that type of decision. But of course, interest rates also do play into it. So both the interest rate and the probability factor in. But just make sure you understand the role of the probability. All right. So again, as long as the probability that the game will end tomorrow is low, then collusion can again be sustained, and we get the same result as we get in the infinitely played games. Now, let's say that you have the opposite case, where the firms know when the game will end. They know exactly when it will end. Like the government has said, we are banning cigarettes in 6 months. In 6 months, no more cigarettes. And so, I'm sorry, I'm sure that hurts some of you. I hope it doesn't. It's not real. You'll be fine. Even though cigarettes are getting expensive, like, how much are they now? They're adding that, or I heard that New York was adding even more, and like they're going up to like $13 or something a pack, or something, which is absurd. I full disclosure, I did used to smoke. I smoked for 17 years. I quit cold turkey about 7 years ago. It was rough, but I did, and it was good. But back then, when I started, cigarettes were only like $2. And when I ended, they were about $5. So they're like $8 now, right? It's ridiculous. Like, I'm sure. Anyway, don't smoke. All right. Anyway, so suppose the game is repeated some known finite number of times. The game will end at some point. So again, you've got that same sort of situation, same kind of pricing scenario. You can charge a low price or a high price. For simplicity, we suppose the game is repeated only 2 times in this case, just to highlight the nature of what's called the end of period problem. So the arguments that follow apply even when the game is repeated a larger number of times, provided the players know precisely when the game will end and the game only has one Nash equilibrium. So the important thing about repeating the game in 2 times is that in the second play of the game, there is no tomorrow. So even though you know that you're going to play the game again tomorrow you know the game will end, and there will be no ability for anyone to punish you for anything you do tomorrow. So each firm has an incentive to use the same strategy during that last period that it would use in a one-shot version of the game. So the one-shot version of the game is basically the final period of any game. And so we know what happens in that one-shot version of the game. The Nash equilibrium is for everybody to cheat on each other and for them to make 0 economic profits. So in the last round of the game, if A cheats in the last round, B cannot punish A for doing so. Firm B knows that A has an incentive to charge a low price in the second period and cheat, and will likewise want to charge a low price in that period as well. Since both players know their opponent will charge a low price in the second period, the first period is essentially the last period. Because everybody knows what everybody's going to do the last period, then, so today, this period, like, there's no way to punish your rival because everybody knows that, well, the only punishment you could enact is to lower the price, which everybody knows you're going to do anyway. So therefore, today is also the last period when there is a last period coming tomorrow. So there is a tomorrow, but it is the last period, and each player knows what the opponent will do in the last period. Thus, in period 1, each player has an incentive to choose the same strategy as in a one-shot version of the game, since they cannot be punished in period 2 for their actions in period 1. So essentially, again, because they know when the game will end, then today becomes the last period no matter what, and we'll just go through one example on how that kind of extends to, like, however many rounds there are, regardless, as long as the game end is known, that same logic will get us to the same situation today as in the 2-period situation. So the Nash equilibrium for the 2-shot version of this game is to charge a low price each period. Each player earns 0 profits during each of the 2 periods. Collusion cannot work even if the game is played 1,000 periods, provided the firms know precisely when the game will end. At that point, any promises to cooperate made during previous periods will be broken because there's no way a player can be punished tomorrow for having broken the promise. So effectively, a player has an incentive to break a promise in the second to last period since there's no effective punishment during the last period. Because all the players know this, there's effectively no tomorrow in the 3rd period from the last. So if you just keep going back the 4th, 5th, all the way to the 1,000th, you get this backward unraveling until the players realize no effective punishment can be used during any period. The players charge low prices in every period right up into the last known period. Quick demonstration problem to just kind of sum it all up. So you and a rival will play the game in the table 2 times. Suppose your strategy is to charge a high price each period, provided your opponent never charged a low price in a previous period. That's a trigger strategy. How much will you earn? Assume the interest rate is equal to 0. So how much will you earn? So you will cheat and hope to get 50, but your rival might also cheat, right? So how much will you earn? You'll earn 0, right? You will earn 0, right? Like, there's just no way around it. So given your strategy, your opponent's best strategy is to charge a high price the first period and a low price the second period. Again, to see why, note that if she charges a high price each period, she's going to earn 10 the first period and 10 the second period for a total of 20 units. She does better by charging a high price the first period, earning 10 units, and then a low price the second period, earning 50 units for a total of 60 units of profit. You're going to earn 10 units the first period, but you're going to lose 40 the second period for a total loss of 30. And so obviously you're not going to do that. And so you're going to do the same thing. And so you're going to wind up in that same situation. All right, just a quick application of this sort of end of period problem. It really applies in a lot of situations. So when players know precisely when a repeated game will end, again, what is known as the end of period problem arises. In the final period, there's no tomorrow, and there's no way to punish a player for doing something wrong in the last period. Consequently, in the last period, players will behave just as they would in a one-shot game. So this section examines some implications of the end of period problem for managerial decisions. Just applying it to the situation where managers have to deal with employees that are potentially quitting. As long as the benefits of not working, shirking, for employees are less than the cost to workers of getting fired, then workers will find it in their interest to obviously work hard. When a worker announces that she or he plans to quit, let's say they plan to quit the next day, the cost of shirking to the worker is considerably reduced. There's really no risk there at that point because they know they're quitting. So therefore, it really doesn't make sense for them to work hard. Pretty intuitive stuff. So since the worker does not plan to work tomorrow anyway, the benefit of shirking on the last day generally will exceed the expected cost. So one possibility for the manager is to fire the worker as soon as he or she announces that they are going to quit. But I mean, aside from like the fact that that's kind of cruel, there might be legal restrictions that stop a firm from being able to do that. So if you if you adopt that kind of strategy where you are essentially ready to fire someone as soon as they tell you they're planning to quit, then employees will ultimately know to expect that. So the best strategy for a worker would be then to wait to tell you when they're going to quit as soon as they are planning to quit versus giving you some advance notice. Consequently, you will not solve the end of period problem, but instead will be continuously surprised by worker resignations with no lead time to find workers to replace them. A better managerial strategy is to provide some rewards for good work that extend beyond employment. So you can emphasize to workers that you're pleased to write a letter of recommendation should a worker need one in the future. This will then send the signal to the worker that quitting doesn't necessarily end the game, essentially. Anyway, it's just one way to kind of apply this end of period problem. It's a very logical thing, but it's maybe not something you thought about before. So again, like it doesn't just apply to the situation we've been talking about. It applies to any situation where, you know, there is some like adversarial type of dynamic and there is an end to your interaction, and you know, and obviously again, like incentives are kind of flipped on their heads when that happens. Like I said, like the benefits to not working go up a lot versus the cost, because there's really no cost in this particular context. Alrighty, now let us move forward to the multi-stage games. So an alternative class of games is called a multi-stage game. We talked about the Stackelberg oligopoly in the last chapter. Remember, we talked about the Sweezy oligopoly. I won't go into that because I've covered it several times. But then we talked about Cournot and Stackelberg. The Cournot was the oligopoly. We considered it again as a duopoly example where there were two firms and they were choosing how much output they were gonna supply in the market at the same time. And so, you know, they had to develop therefore a reaction function, a way to figure out how they should optimally choose their output as a function of how much their rivals would choose. And then the interaction of the two firms' reaction functions got them to this equilibrium level where each supplied a certain amount, and it wound up being the same if they both had the same marginal cost. But that whole thing changed when one firm was able to move first. If one firm was able to move first and choose their output, then that really did change the outcome. That firm wound up having a big advantage in those markets. They wound up being able to supply more. They wound up getting bigger profits. So it completely changed the outcome. And so that obviously is just a slight reflection of how, you know, making decisions at the same time differs significantly in terms of outcomes than situations where decisions are made sequentially, where people have time to react to their opponents, etc. So that's sort of what this approach will highlight in terms of that characteristic. All right, so multi-stage games differ from the class of games examined earlier in that timing is very important. In particular, the multi-stage framework permits players to make sequential rather than simultaneous decisions. Let's look at the theory. To understand how multi-stage games differ from one-shot and infinitely repeated games, it is useful to introduce what's called the extensive form of the game. So what we've been doing so far, looking at the games on the table, that's again called the normal form of the game. When we're looking at multi-stage games, we are looking at what's called the extensive form of the game, which is like a game tree, as you'll see right now. So an extensive form game summarizes who the players are, the information available to the players at each stage of the game, the strategies available to the players, the order of the moves of the game, and the payoffs that result from the alternative strategies. So the best way to understand the extensive form is via an example. So here is an example of an extensive form of the game. So the circles are called decision nodes. So this is the decision node for player A. Player A begins the game, can either go up or down. These are the decision nodes for player B. And player B can react to either the decision to go up or go down, and they can set up a contingency plan for it. They can say, well, if player A plays up, I'll do this. If player A plays down, I'll do this. So again, the single point A at which all the lines originate is the beginning of the game. The numbers at the end of the branches represent the payoffs at the end of the game. So again, you've got numbers in parentheses. The first number represents the payoff to player 1, which is A in this case, and then 15 represents the payoff to the second player, player B, in each of these outcomes. So this is the payoffs if player A plays up and player B plays up in response to that. Therefore, player A would get 10 and player B would get 15 in that case. In this game, player A moves first, and player B must respond with a move. As in simultaneous move games, each player's payoff depends not only on his or her actions, but on the actions of the other players as well. So again, it just does capture the interdependence in decision making. But again, A cannot make a contingent decision based on what their rival will do. Like, they have to just decide what to do. But their rival can threaten to do one thing or something else prior, of course. So again, the difference between the sequential move game and the simultaneous move games examined in the previous sections is that the first player, player A, cannot make actions conditional on what B does. I said that already. In contrast, B gets to make a decision after A. So consequently, a strategy for B will specify an action for both of its decision nodes. So again, the strategy for B will be basically a contingency plan depending on what they think A will do. To illustrate how strategies work in these sequential games, suppose that player B's strategy is choose down if player A chooses up, and choose down if player A chooses down. So again, if player A chooses up, B is saying, I'm going to choose down. And if player A chooses down, again, B is saying that I'm going to choose down. Based on the numbers we see here, does that make sense? Why? Right, so B is saying that if A chooses up, then they're going to choose the option that's going to be worse for them, right? Which, again, is not rational in terms of how we define rationality in economics, which means that people are always choosing the option that benefits them the most. So by B saying that, they are not being rational. They're basically not making a rational decision. But let's just say that that is the strategy for now. So given the strategy, A must consider what her best strategy is. So there might be a reason why B said that they would do that. And the reason, if we look at all the possible payoffs, might be about them trying to get the highest possible payoff, right? So we can see that the payoffs for B are 15, 5, 0, and 20. Obviously, 20 is the highest. B wants 20. So how is B going to get down here? Well, B needs to get A to choose down, right? And therefore, if B threatens to choose down if A chooses up, then that means that A would wind up with 5 as opposed to 6. right? And so that creates an incentive for A then to say, okay, well then I will choose down or else I'm going to get hurt. But again, it is contingent on the idea that B would make a decision that's against their own best interest. So again, given a choice between earning 5 and 6, player A prefers 6 and therefore will choose down. Given that player A chooses down, then the question is, does player B have an incentive to change his strategy? Player B said that she would choose down if player A chose down. Would player B change their strategy if that happened? No, they wouldn't, right? Because, again, faced with the option of picking up and getting 0 or picking down and getting 20, obviously they're going to choose 20, right? All right, since neither player has an incentive to change his or her strategies, we have found a Nash equilibrium for the game. So a Nash equilibrium for the game basically involves B saying, I'm going to choose down if A chooses up, and I'm going to choose down if B chooses down, and then A saying, well, then I'll choose down. So that results in this Nash equilibrium for the game. So these strategies are, again, player A down, player B down if player A chooses up, and down if player A chooses down. So that's how you would write the Nash equilibrium for the game. But then the question is there a more reasonable outcome for the game? A up, B down? A up, B up would be better, right? So A would choose up, and then B would have to choose between up and down. Obviously, 15 is better than 5, right? So they would wind up choosing up in the end. So that is a better outcome for the game. A would wind up with 10, and obviously happier. And B would not get as much as they would get in their Nash equilibrium. But then again, they don't have that first mover advantage. So they really can't force the game unless, again, they make that threat. But then the question is the threat credible? So notice that the highest payoff for player A results when A chooses up and B chooses up as well. Player A didn't choose up because player B threatened to choose down if A chose up. But then the question is, should A believe this threat? And we've established that no, player A should not believe this threat because obviously that means that B would be working against her own interests in that case. So this reveals that there is, again, another Nash equilibrium for this game, and it is that outcome there. So in this Nash equilibrium, A chooses up, and then B chooses up if A chooses up, and B chooses down if A chooses down. So in this Nash equilibrium, again, player A earns 10 and player B earns 15. Which of the two equilibriums is the more reasonable one? Well, we've already established that. It is definitely this one, right? It is the one where everybody's kind of behaving rationally, and A is taking advantage of their first mover advantage. So again, it is that second one that we just established. So the reason is as follows. In the first Nash equilibrium, player A chooses down because player B threatened to play down if player A chooses up, but player A should recognize that this threat is not really credible. So in the jargon of game theory and the terminology of game theory, the Nash equilibrium in which player A earns 6 and player B earns 20 is not what's called a sub-game perfect equilibrium. So a set of strategies constitute a sub-game perfect equilibrium if it is a Nash equilibrium. And at each stage of the game, neither player can improve or pay off by changing her own strategy. So basically, a sub-game perfect equilibrium is a Nash equilibrium that involves only credible threats. But the threat can be made by player B before the game even starts, and therefore, if A were to buy that threat, then that would get the game down here, and therefore that would be another outcome for the game in which neither player would have any incentive to deviate from at that point. Because again, A believes that they would wind up here, therefore they choose to go this way because they know they'll wind up here, which benefits them more. And then once that happens, B will choose the option that benefits them most, and therefore the game would result in this outcome. So it is a Nash equilibrium, but it is not a sub-game perfect Nash equilibrium because it involves a non-credible threat, the threat of choosing down, where in reality, if we look at the payoffs, we know that B would not choose down. So the only subgame and again, that is all contingent on the assumption that the players are going to behave rationally. Obviously, in the world we live in, that doesn't always happen. We have a president that is a very clear result of that. You have a lot of people in this country that chose to vote for somebody who is not going to look out for their interests and is now, piece by piece, slowly dismantling the government that helps and supports them. And so, people don't always have all the information they need to make a rational decision, or maybe something is clouding their ability to understand what is the right choice for them. So that's why, again, this is all very simple analysis. We have a branch of economics called behavioral economics, which focuses on this issue of like rationality and like what makes people behave in the ways that they do. And that's ultimately what winds up screwing everything up in terms of like, what maybe we can predict in our discipline versus what actually happens in the economy, which is why, we'll get like recessions every now and then and just like crazy things happening, crashes of the stock market, etc., because people will make decisions that don't make sense, and that will result in outcomes that cannot be predicted, right? So that's why, again, economics is an art versus a science, because at the heart of the system we are studying are people that cannot always be counted on to do the right thing for themselves, right? It's just reality. We all know it. We all make the wrong decisions for ourselves all the time. So but we're all guilty of it. All right, so the only and hopefully you won't be guilty of it these next few weeks when you're studying for your finals and getting ready to get good grades. Like, you'll choose the right decisions for yourselves, but some of you aren't. Those people in those empty seats. All right. So so again, we're talking about the subgame perfect equilibrium, and a subgame perfect Nash equilibrium involves only credible threats. So the only subgame perfect equilibrium involves player A choosing up and player B then also choosing up. All right, so let's do some examples of these multi-stage games. The first one is the entry game. So one thing to note, like normal form, extensive form, if I give you information about the environment and what's going on in the game, payoffs, strategies, players, you should be able to set up the game. So make sure that you can do that. Both types of games. All right, entry game. So to illustrate the use of the theory of multi-stage games in a market setting, consider this extensive form of the game. So here, firm B is an existing firm. They're already in the market. And firm A is a potential entrant. So kind of mirrors the excludable market situation that we talked about at the end of the last chapter, where we also know as contestable markets, where there's like a firm operating in the market and they're always operating on the threat of another firm coming in, and under certain conditions that will drive the existing firm to not use their monopoly power and basically charge the lowest price possible, where their price is equal to marginal cost, because they're always being threatened by the entry of another player that will come in and undercut them at any time. So that was the contestable market situation. So this is somewhat kind of reflecting that kind of situation where you have, again, an existing firm and then another firm that's thinking of either entering or not entering. So firm A has to decide whether to enter the market or not. If A decides to enter the market, B must decide whether to engage in a price war and compete in a hard way. So that's what the hard signifies. Or just kind of share the market with their rival and play softly, as it were. So the payoffs are measured in millions. If player A chooses to stay out, then obviously they don't get anything, but player B winds up with good amount of profits, 10 million. If player A chooses to enter the market, if player B chooses to play hardball with them and severely undercut them, A will wind up losing, and B will have to give up profits in order to do that because they have to lower their prices. Or B could just say, all right, fine, I'll accept you're in my market now, I'll share the market with you, and that's it. They'll split the profits, which is 5 million each. In this game, there are two Nash equilibria. So the first occurs where B threatens to choose hard if A enters the market, and thus A stays out of the market. So again, B would choose to would threaten to choose to play hard, right? Is that a credible threat? No, it is not a credible threat. Why is that? -1 is less than 5, right? I'm sorry, 1 is less than 5. So again, we're talking about the payoffs to player B. So 1 is less than 5. So in that case, they would have to choose the option that hurts them, which is not a credible thing that you would assume a firm would do. Yeah.
Still credible because it's still going to be above 0. Well, the person just actually market will be.
So
they will operate at very little profit while you operate at.
So that's assuming that there's further rounds and that they'll be able to then maybe get their price back up once the threat goes away. Given that scenario, yes. But given just what we have here, which is always what you should be thinking about in the examples, they have an option to either do that and get 1 million versus not do that and get 5 million. So that's 4 million less. So they're giving up $4 million. If there's subsequent rounds, then yeah, because then they could reap the extra benefits over time. But we're not assuming that here. So just keeping it simple, just to be able to identify the Nash equilibria and the subgame perfect Nash equilibria. But yes, it's good to think like that, but not in the examples. But good stuff, yeah.
Adding to what he said, basically, if it did keep going, would it be smart to choose that so that you eventually kick A out of the market?
Yeah, exactly. Yeah, you're gonna want to undercut them, hurt them, so that they aren't able to compete and they're not able to make profits, and then you get the whole market again, and then you get.
They have said it would be -1, and that won't hurt much. Or there is a formula where they can calculate how much is getting correct.
So the -1 is how much the entrant would.
-1 and making 1. So same value.
Well, but you're talking about a loss of $1 million to a firm that it has. B is making $1 million, right? Right.
But to get it out of the market, how much A would have to be hurt?
Well, that's up in the air, right? That's it. We can think of a lot of scenarios. We could go really far with this. We could spend a week talking about this, and I love that you guys want to, but we shouldn't. But yeah, like obviously, ultimately depends on like how much they're willing to like lose. You know, how much are they willing to endure if indeed that happens? Because they know that ultimately that their rival is getting hurt as well. So obviously it's a complicated situation, but this is just a simple way of analyzing whether or not a firm will or will not enter, considering the initial sort of result. And given that there's only 2 rounds, that implies that that's all that they can really endure in this context. So let's just keep it simple, but it's great. I mean, I don't put it past any of you to be able to think a lot further than this. I know we could all come up with really great scenarios and really great strategies, and good stuff, folks. All right. Anyway, so let's just continue thinking within the simplicity of the problem. So again, that is a Nash equilibrium where again. B threatens to choose hard if A enters the market, and thus A then either has the 2 options of losing $1 million or just staying even. Obviously, staying even is better, so they would choose that. So they would choose to stay out. So that is a Nash equilibrium for the game. So again, to see that these strategies indeed comprise a Nash equilibrium, note the following. Given that firm B's strategy is to choose hard if firm A enters, A's best choice is not to enter. Given that A doesn't enter, B may as well threaten to choose hard if A enters. Thus, neither firm has an incentive to change its strategy. Firm A earns 0 and firm B earns profits of 10 million. All right. So again, this Nash equilibrium, though, involves a threat that is not credible. So therefore, it is what kind of Nash equilibrium? So it's not a subgame perfect equilibrium, right? Not a subgame perfect equilibrium. So subgame just referring to the fact that, like, you know, this could be considered like the game, the first game, and this is like the subgame, right? In the subgame, it's not perfect because we're assuming that somebody's going to make a decision that's not rational. So the reason firm A chooses not to enter is that firm B threatens hard if A enters. Does B have an incentive to carry this threat out if of choosing hard if firm A enters? Well, we know that's not the case. So obviously, firm B would not choose that, given the simplicity of the problem that we're talking about. So the answer is no, again, since given that firm A enters the market, firm B will earn $5 million by choosing soft, but only $1 million by choosing hard. All right. So if firm A enters, it is not in firm B's best interest to play hard, and that's why we get that outcome. And again, that's why it is not a subgame perfect equilibrium. I have to edit these slides. I haven't edited them. I haven't gotten a chance to get a lot of this stuff out, but anyway, you guys get the point of what's going on. So again, it involves a threat that is not credible, namely the threat by firm B to engage in a price war if firm A enters. The other Nash equilibrium for the game is for firm A to enter and then for firm B to play soft, obviously. Because, again, that would be the best outcome for firm B given the fact that A would, at that point, choose to enter. So in particular, if A enters, firm B's best choice is to play soft. B earns $5 million instead of $1 million. It would earn by playing hard. Given that firm B plays soft, if firm A enters, A's best choice is to enter. By choosing to enter, they wind up with 5, which is better than 0. So this is a sub-game perfect Nash equilibrium because it is clearly in firm B's self-interest to play soft when firm A chooses to enter. Thus, while there are, again, 2 Nash equilibria for the entry game, Nash equilibria, a set of strategies that neither player has any incentive to deviate from, there is a unique sub-game perfect equilibrium in which firm A chooses in and firm B plays soft. So the concept of the subgame perfect Nash equilibrium versus the imperfect subgame equilibrium is important. It's an important one because you need to be able to identify the fact that the game could result in that, and so it needs to be acknowledged, and then you need to think, okay, well, will they actually follow through with the threat, right? All right, another possible application is the decision to either create a new product or not to create a new product, and to compete against an existing product. Actually, no. In this case, it's to create or not create a product, and then the other firm needs to figure out if they are going to clone the product, I think. Anyway, so an analysis of the entry game reveals an important lesson for future managers. It does not pay to heed threats made by rivals when the threats are not credible. We can also use the theory of sequential or multi-stage games to analyze innovation decisions, as the next problem illustrates. All right, so your firm must decide whether or not to introduce a new product. If you introduce a new product, your rival will have to decide whether or not to clone the new product. The payoffs are given in millions. The negative loss represents a loss in research and development that must be spent in order to create the product, but that obviously would not need to be spent by your rival, who can just take the product and clone it. So the question is, should you introduce a new product? So you're asked to set up the extensive form of the game. How would your answer change if your rival has promised not to clone your product? What would you do if patent law prevented your rival from cloning your product? All right, so these are the 4 questions we'll consider. We are given the payoffs, of course. If you don't introduce the new product, you and your rival will each earn $1 million. If you introduce a new product, your rival clones it, then you lose $5 million and your rival earns $20 million. If you introduce a new product and your rival doesn't clone it, you earn $100 million and your rival earns 0. So this is all the information you would need to set up the extensive form of this game. So make sure that you are able to do that, and also, like I said, set up a normal form of the game and understand the difference between the two so that you don't get mixed up. All right. So we're going to set up the extensive form of the game here. So again, A can either introduce or not introduce the product. If A does not introduce the product, then both firms wind up with, let's say, $1 million. If they introduce a product, then B can clone the product, which means that A loses the research and development money and B reaps the profits of selling the product without having to spend any money to develop it. Or B could not clone the product, in which case A gets all the profits. All right, so should you introduce the product? So it depends, right? It depends on what the other player says they're going to do, right? Or what you think they're going to do, right? So if you introduce a product, again, B's best option would be obviously to clone, right? Given the situation. So they would wind up making 20, and you would wind up making -5. So in comparison to that, you can either not introduce a product and just keep your 1 million, right? So obviously, what should you do? Not introduce the product, right? Yeah.
It's like taking into consideration like legal issues or like contracting concerns, like oh, only this place can have this product.
So like patent laws.
Patents or like.
So we'll consider that. We're going to consider that in like the third question. So again, if you don't introduce a product, you will earn 1 million. Thus, your profit maximizing decision is not to introduce a product, obviously. So how would your answer change if your rival promised not to clone your product? So the rival promised not to clone the product. Well, I mean, just let's work under the assumption that they're being honest, yeah. But we know they're not. Let's say they're being rational. Let's say they're being rational, right? If they're being rational, they're not going to do that, right? So therefore, would you introduce the product?
Yes.
You would, because they said they're not going to clone it. There's no contract. They're just saying it.
No, it's a trade away.
They're a firm that can make $20 million or make zero, and they're saying, "Oh, sure, we're not going to make $20 million."
No.
Are you going to believe that? No, right? So if you believe your rival's promise not to clone, you will earn 100 million by introducing the new product and only earn 1 million if you don't introduce it. However, B's promise is not credible. We know that. So B would love you to spend the money developing the product so that then B could clone it and earn profits of 20 million. So again, we're not assuming patent laws or anything, any kind of protections yet. So again, in that case, you do stand to lose 5 million, which obviously is less than 1 million. So since the promise is not credible, you had better think twice about letting it affect your behavior. All right, what would you do, though, if patent law prevented your rival from cloning your product? Introduce a product, right? Now we're talking about legal protections. Now we're talking about the ability to introduce a product and being able to reap the rewards from that without anybody being able to steal your product, basically. At least initially. We know that in practice, people do reverse engineer things. International law doesn't always protect patents, so even though you might have a patent in the US, that may not apply internationally, so anyone beyond our borders could clone your product or whatever. But trade deals tend to protect that stuff as well, which someone's trying to dismantle. If you obtain a patent on your new product, B will be forced by law to refrain from cloning. In this case, you should introduce the product to earn 100 million, obviously. Okay, so this illustrates that the ability to patent a new product often induces firms to introduce products that they would not introduce in the absence of a patent system. So it just highlights, like, obviously the importance of a patent system, but as I mentioned before, patents are a way for firms to gain monopoly power. And so there is that trade-off in our society that if we allow firms to have patents, we have to allow them to have monopoly power, which means that we're going to have inefficiency, we're going to have high prices, low quantity transacted in those markets. But if we don't have the incentive for firms to do that, they won't spend money on R&D and innovate. And if you remember your macroeconomic course, ultimately, long-term macroeconomic growth, which is what raises the living standards in any country, is purely dependent on the advancements in technology. And so we have this kind of weird situation we're all in. We all just kind of have to live with it. All right, let's look at the final example, the sequential bargaining game. So we looked at a bargaining game last week in which, again, there was a union and management, and they were trying to figure out how to divide up a surplus. And we saw that in that situation, when the players played simultaneously, that we wound up in 3 different Nash equilibria, and therefore it was difficult to say what the best outcome is. And it just kind of highlighted the fact that, like, those kind of negotiations often lead to like kind of a stalemate, and we saw it last year here with we got very close to a strike. The writers' strike, the writers' union in Hollywood right now is threatening a strike. They had a writers' union. They had a writers' strike, I think, like about 8 years ago. Lasted a few weeks. I know. I saw an analysis. It like hit the city like in the billions of dollars in terms of revenues because films didn't get made, people didn't work, and we actually wound up getting a lot of really bad movies because the writers weren't there to write, which is a bad thing in and of itself. Anyway, so yeah, it's complicated, but this will highlight how like if there are stages, then it does kind of change the outcome a bit. So specifically, suppose a firm and a labor union, again, are engaged in negotiations over how much of a $100 surplus will go to the union and how much will go to management. Suppose management moves first by offering an amount to the union. Given the offer, the union gets to decide to accept or reject the offer. If the offer is rejected, neither party will receive anything. If the offer is accepted, the union gets the amount specified and management gets the residual. To simplify matters, suppose management can offer the union one of three amounts, $1, $50, or $99. Again, we just assume there's $1 in administrative costs. So notice that the union gets to make its decision after it learns of management's offer. So again, management can make either one of three choices. And of course, that complicates the game tree a bit. It provides then three different contingencies that the union has to consider. And again, this is just a very simple example of this type of analysis. We can extend it to more complicated situations where there are more than two stages and the game trees become really big. But again, like it really helps you to maneuver. Like if you have situations in your life where you have these kind of situations where decisions are being made, like it might be good to just kind of work it out in a game tree. And like the numbers, they just kind of have to reflect like, like the relative benefits and costs to an outcome. Like they don't actually have to mean anything. So you can use this tool to kind of figure things out that are like complicated and like involve a lot of people making decisions, and you just, you're kind of lost in those situations. Anyway, notice the union gets to make its decision after it learns of management's offer. Suppose you are management and the union makes the following statement to you before you make an offer. Give us $99 or else we will reject the offer. So the union is saying that. Give us $99 or we will reject the offer. So basically, management can choose $1, union rejects, they get 0. Choose 50, union rejects, get 0. So if the union is saying they are going to only accept the offer if management makes $99, then in that case, at the very least, the management will get $1, right? So that is one of the Nash equilibriums for the game, therefore. But obviously, it is not a what? It's not a subgame perfect equilibrium, right? Because it involves a non-credible threat. The union is saying that they will reject any other offer, even though rejecting any other offer would mean that they would wind up with 0 versus $1 or 50, right? Which obviously is not something that they would want. So what should you do? So if you believe the union, then if you offered it a lower amount, it would reject the offer and you would get nothing. If given the union strategy, your best choice is to give the union $99 since the action gives you a payoff of $1 instead of 0. And given that you offer the union $99, its best choice is to accept the offer. Thus, one Nash equilibrium outcome of this sequential bargaining game is again $1 for management and $99 for the union. Does this mean the optimal action for management is to give the union the $99? No, it's not, right? Because the management needs to consider, what are my options? What are my best options? Well, I can either wind up here, get 99, here get 50, or here get $1. Obviously, they want to wind up here. So they would therefore offer $1, and then they know that the union would, of course, accept it because it's better than 0, right? So they would wind up with 1, and then management would wind up with 99. So therefore, this is also a Nash equilibrium, and it is a subgame perfect Nash equilibrium. So again, notice this equilibrium is supported by a union threat that's not credible. That's the original one. This is all right. Anyway, that's everything I said. All right, now let's just look at the last demonstration problem, just kind of switching the roles. The union gets to go first. Management then responds to the union's decision. But like Again, accepting or rejecting leads to the same type of situation. So consider the bargaining game just described, but suppose the order of play is reversed. The union gets to make an offer, and then management decides whether to accept or reject the offer. What is the sub-game perfect equilibrium outcome of this bargaining process? Is it 50? Because the union gets to go first. Right, exactly. It would be the 99-1, right? Like the union gets to go first. They're going to try to get the outcome that's going to benefit them the most, which is that one. So they're going to offer $1, and then management will have to accept it, or else they'll wind up with 0, right? So that is, of course, the outcome. So the profit maximizing choice by management is to any offer is to accept it if it yields more than 0, because management would earn more than 0 that the management would earn if they rejected the offer. Therefore, the subgame perfect equilibrium is for the union to offer management $1 and to keep 99 for itself. You guys, I think, were thinking in terms of fairness when you chose this one here. Again, we're not talking about fairness, equity, ever in this class. We're talking about efficiency, right? And efficiency for markets is about people making rational decisions for themselves, even if it's not fair in terms of like what we normally would ethically think is fair, because obviously firms don't operate under an ethical code. In general, it's true. This is the reality of life. All right, so given this offer, management's best choice is to accept it. Any threat by management to refuse an offer of $1.50 would not be credible. And that's that. Let's just end it there. All right, well, we're done with this chapter 2. We have 2 more chapters to go. Again, I'm going to open up this mini paper for next Thursday. That's the last one. Beyond the mini paper due Sunday. That's open chapter, any chapter. And then, again, the ball is in your court. Work hard. Work really hard. But, again, have a good weekend. I'll see you on Tuesday.